Welcome to the Explainer. Today, we're going to put on our detective hats and solve a pretty common mystery.
Well, the first step isn't some super complex, high-tech forensic technique. It's actually much simpler. It's just about getting to know your evidence. And this simple idea, it's the core of our entire investigation today. Okay, let's break this down. The official term is Exploratory Data Analysis, or EDA. Think of it as our official investigative toolkit. It's the whole process of using visuals and some basic stats to really dig into a data set. We're looking for patterns, spotting anything that looks weird or out of place, we call those anomalies, and just generally checking our assumptions before we even think about doing any heavy-duty modeling.
Every good detective starts the same way, right? They take each piece of evidence, one by one, and look at it under a magnifying glass. In the world of data, we do the exact same thing. We call it univariate analysis, and it's all about looking at just one variable at a time.
To make this all feel a bit more real, we're going to use a simple student data set for our case file today. Inside, we've got clues like age, gender, how many hours they studied, and their final exam score. So, let's start by grabbing just one of those clues and putting it under the microscope, the age of the students.
Okay, so the most basic thing we can possibly do is just count stuff. This is a frequency table. It shows us how many students fall into different age brackets. I mean, it's useful, I guess, but it's not exactly easy to see what's going on, is it? It's really just a list of numbers.
But now, look what happens when we visualize that same data. We take that boring table and turn it into a simple histogram. Instantly, I mean right away, you get a feel for the shape of the data. You can see the whole distribution of ages in our classroom. We can see exactly where most students are clustered just at a glance.
So, just by looking at that one single variable, we've already gathered some critical intel. We know its frequency, how often different ages pop up. We understand its distribution, its shape, and we can start to spot any potential outliers. Like if there was one student who was much older than everyone else. That's a clue that might be really important to our case later on.
And here's a really important point. The tool you use, your magnifying glass, really depends on the type of clue you're looking at. For categorical clues, things you can sort into buckets like gender or favorite subject. We use tools like bar charts and pie charts. But for numerical clues, things with numbers like age or exam score, our go-to tools are going to be histograms and box plots.
All right, so we've examined our clues one by one. Now for the fun part. Let's see what happens when we start connecting them. This is called bivariate analysis, and it's where we look for relationships between two pieces of evidence at a time.
When we're doing bivariate analysis, we're always looking for relationships between two variables. And it turns out there are really three main types of connections we can look for, and it all depends on what kind of clues we're trying to match up.
So let's tackle that first matchup. What happens when you compare two numerical clues? For example, let's ask a question. Is there any connection between the number of hours a student studied and the final exam score they got?
Now, when we plot this out, with hours studied on one axis and exam score on the other, a pattern jumps out at us almost immediately. You can see this clear upward trend. It looks like the more hours someone studied, the higher their exam score tended to be. See, the clues are starting to connect.
And this is where statistics give our investigation some serious firepower. We don't have to just go with our gut feeling from a visual. We can actually calculate the strength of this relationship, a number called the correlation coefficient. When it's close to +1 like this, plus 0.97, well, that tells us there's a very strong positive connection between our two clues.
And, just like before, we've got specialized tools for the other matchups too. We can use things like contingency tables to compare two different categories. Or we could use box plots to compare a number, like exam scores, across different groups. Say students who studied alone versus those who studied in a group.
Okay, so we've looked at clues by themselves, and we've looked at them in pairs. Now, it's time for the big reveal. Let's zoom out, see the whole picture, and really understand how multiple clues work together to tell the full story.
This is where multivariate analysis comes in. It lets us ask much more complex questions. For instance, how do age and gender together influence exam scores? A heat map like this is perfect. It lets us organize the data to see the average scores across all these different subgroups at once. You start to see patterns you would have totally missed otherwise.
You see, by looking at multiple variables all at once, we go from just finding simple connections to really understanding a complex system. And that's the ultimate goal of any good investigation, right? To see the whole story, not just a few insulated incidents.
Okay, so we've walked through the whole process. But you might be wondering, why does all this detective work actually matter? I mean, why can't we just jump straight to the fancy machine learning models and algorithms?
So let's just quickly recap our investigation. We started by looking at single clues with univariate analysis. Then we found connections between pairs of clues with bivariate, and finally we put it all together to see the complete picture with multivariate analysis.
And believe me, this process is absolutely essential. This kind of detective work helps you spot obvious errors in your data right from the start. It helps you uncover hidden patterns and relationships you never would have seen otherwise. It guides you in choosing the right analytical tools for the job. And all of that ensures that your final conclusions are actually valid and that your models are built on a solid, reliable foundation.